the symbol we use for inductance is a capital L. So the EMF, if I'm dealing with a solenoid that is, or if I'm dealing with an inductor, and if I forget, remind me to explain the difference between a solenoid and an inductor, is negative L delta I over delta T. So this will be the strength of the induced EMF, which should indicate, if I know the resistance, put a little 2 down there, because this is going to be a secondary current, and this is the primary current. This one, I'll put a little 1 there for the primary current, 2 for the secondary current. It's going to be equal to I2R, just overall. So it so happens, just coincidentally, the next lab is you'll be working with us. You're going to figure out what that is, and you're going to figure out what that is, and you'll you'll measure that, and you're going to make a prediction about what that current should be.
Is that
In
a
essence,
2 subscript on that IR?
that's a 2 there because this is the change in the initial current, whatever is coming from the power supply. This is the induced current. Questions to hear? And sort of a heads up, the lab that you were going to be doing, the lab that you will be doing, the original version of it, 10,000% error or difference was not uncommon. I changed it. It's now under 100%. So it feels like a vast improvement, but actually if you take time and care, you can get it under 20%. So, something to look forward to. However, the lab after it, that's the one where there's one part, if you get over 1% error, you've done something wrong. So, something to look forward to. Units. The unit of inductance is the Henry. Named after Henry. Hank to his friends. No, Henry's his last name. For those people who play Words with Friends or Scrabble, this is just a side note. There is an inverse Henry. So 1 over a Henry is a never actually heard it pronounced, but I always pronounce it Irna. It is just Henry written backwards. It is a legitimate word. Another legitimate word is that there is such a thing as an inverse ohm, which is a mo. These are both legitimate Scrabble words, or Words with Friends.
No. Are they units?
Yeah, they are units.
Okay.
I've never actually seen them in use. I've read about them, but
Inverse.
yeah, generally instead of mo, you would write the omega with a -1 there, or the Henry with a -1.
Have you used these words in a Scrabble game?
I've used Irna in a Scrabble game. I'll come back to that. I was gonna jump into the next thing, but that might be the next chapter. RBC. Magnetism. That's a lot of RBC stuff there. Okay, that is the next chapter. Okay, I will wait. Questions? Now, hopefully you can see some sort of importance to inductors if we have, because remember, the inductor comes in handy, I still have to talk about that versus solenoid. An inductor comes in handy if the current is changing. We, in the US, well, actually pretty much all over the world, current is constantly changing. In America and Canada, it's going back and forth. In Europe, they have DC, but it's still changing. It goes fast and slows, fast and slows, fast and slows, sort of always going in the same direction. Since current is constantly changing, we have potential for a whole lot of secondary induced currents being created because of this whole bit. But before we get too far into AC, which is what we're branching into, there's two big concepts that we do need to get across. Number one, I'm assuming most of you have had some trick, as well as we probably would have hit it in 151. What is this?
A sine wave.
All right. So if this is, we'll just call this position versus time. Why not? If that's position versus time, what would the velocity versus time graph look like?
It'll be positive when position is going, when the first graph is going up, it'll be negative when the first graph is going down.
All right, so it's going up to start with, so it's positive. It's 0 there. It's most negative there. It is 0 there, and then it is positive, so it's going to look like that is horribly drawn. That is just marginally better, but not a whole lot. But what is that graph?
Cosine.
Yeah, so this is sine, this is cosine. What will the acceleration versus time graph look like?
It'll be a negative sine graph.
It starts out at 0, then it goes negative, then positive, and then back to 0 again, so this is negative sine. And so that's acceleration, and what does the jerk graph look like?
Negative cosine.
So it starts out negative, goes to 0, peaks. What would the snap graph look like?
Back to sine.
Would it look like what?
A sine graph.
And then back up here. So the sine graph and, sorry, the position graph and the snap graph would look similar. Crackle?
Same as velocity. Same as velocity.
And pop?
Same as acceleration.
Yeah. Well, it's similar too.
So, well, yeah. Same,
There are other things that could change it.
same function.
Say it again?
Same function.
Yeah, same basic function. All right. So if I have something oscillating back and forth, it'd probably be really helpful if we had some idea about sine, cosine, the fact, this pattern here of sine, cosine, negative cosine, back to sine, and so forth. wherever I start, I can start at negative sign, there goes a negative cosine, sine, cosine. If you've had calculus, this would probably be second nature. But we do have the pattern, sine, cosine, negative sine, negative cosine, and then back again. The other thing, which might seem like a completely separate idea, is this idea of a phasor. A phasor has a lot of similar characteristics to a vector, but a phasor sort of spins. Think like so many kids' games with a spinner on it. You just think of an arrow and you flick it, and the arrow goes spinning around like that. So a phasor is like a vector with one end fixed, and it rotates around like that. As an arrow spins, how would you describe its motion? What words would you use to describe its motion as it spins?
Rotational.
Okay, rotational what?
Clockwise or counterclockwise?
Okay,
Oh,
looking for the quantities, measurable quantities.
angular velocity.
All right, angular velocity. The symbol for angular velocity?
It's the weird looking W, I don't remember which one it was. Is that omega?
Those are the
Lowercase omega?
units. Say it again?
Is it a lowercase omega?
It is indeed. Is that what you were saying? So angular velocity. Now, it's always going to be spinning with a rotation. If this were actually a spinner, it would always be spinning with the angular velocity pointing outwards. It does move around in a counterclockwise direction. Classic math where 0 degrees, 90 degrees, 180, and so forth. Or we're more sophisticated and we're cool. 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, 2 pi radians, or 0. At some angular speed, omega, it also spins around with a certain frequency. And the angular frequency is equal to omega. There's a philosophical difference between those two omegas, but the value is going to be the same. The angular speed with which that is spinning corresponds to the angular frequency.
If we have, I have no clue if you have a question with the phasor, but is it always going to be in radians?
Most likely.
Okay.
Flashing back to the problems that we'll be hitting. Yeah, probably. Yeah, make sure your calculator is set right. All right, we got the background, as well as the past couple months.
Did you talk about the difference between a solenoid or something?
Oh, thank you. I was once giving a talk and I said, I will get to this later, and at the end of it, I forgot completely that I was going to talk about it. And they asked me one question, and that was the question of what I said I was going to talk about. Oh well. Glad to know that my symptoms are not worse than they used to be. They're just as bad. All right, so solenoid. So a solenoid can be used as an inductor. It's got a current running through it. If the current changes, we're going to get a change in the magnetic flux, which would create an induced current. Typically in a device, the biggest difference between the solenoid, what's being used as a solenoid and what's being used as an inductor, is that an inductor has a much thicker wire. Because it is a thicker wire, it's going to have lower resistance. Solenoids, at least my experience with them, is that they are thinner wires, greater resistance, and so resistance has more of an impact. So The solenoids that we have, if you look at the specs, it tells us that it gives us a value for the inductance. So the solenoids can be used as an inductor, but they're just high resistance inductors. That's the difference. Whereas inductors generally are much lower resistance. And now back to this. If I have a simple circuit here, where I've got my AC power supply and I have a resistor. Since my AC power is fluctuating back and forth, we can somehow describe it as the EMF is equal to EMF sub 0 times, and it's either going to be a sine or a cosine. It's one or the other. I'll just do sine for right now. Sine of omega t plus phi. And I'll make sure I wrote that in really tiny print so that people in the back with bad eyesight will wish they had sat closer. Epsilon is equal to epsilon sub naught sine omega t plus phi. So, and I do need to change this.
Does the epsilon sub naught, it just makes me think of if we're gonna do free space, is the epsilon, the sub naught. Is that related to the wire it's going through?
No. Are you thinking of permittivity?
Probably.
Yeah, it's not related. It's,
Different?
yeah, that's not the epsilon, that's not U1.
Totally different.
Yeah. Again, we've run out of letters. This right here is the maximum voltage. Now, when I said I need to change this, and I wrote it again, it might, to some of you, look like I just wrote the same thing I had before. The difference is this is smaller. And so, the typical tradition is that when you're talking about instantaneous values, so for AC, instantaneous voltage or instantaneous current, the value at a specific moment, you use lowercase. Uppercase tends to stand for some sort of constant. So the maximum voltage should stay the same, assuming your power supply is proper. So that's why that's an uppercase. In terms of phasors, that capital epsilon sub naught, that is the magnitude of the phasor. So if I mapped it out, if I had epsilon sub naught, that is the length of, that would represent the length of that, or the length of that represents epsilon sub naught. As the phasor spins around, the projection onto the horizontal axis, this would be the instantaneous value. So if you imagine I have a giant light up above, it's shining down and it casts a shadow, it's the length of the shadow. Omega, well, you tell me, what is the omega in my equation over there?
Angular speed or frequency?
If it's, you're saying angular speed, what is the angular speed of?
The
Phasor?
phasor.
Yep, as it spins. And phi? Flashback to math class here, what is phi?
The angle.
Of
Phasor.
when?
At instantaneous.
No, not at instantaneous.
Related to where it is, like in the x-axis? Or like at
When?
where it starts?
Where it starts. This is called the phase shift. In a lab, when you're doing the measurements where you have the, it's constantly changing, you thought that you would hit it perfectly when it is on an axis. Odds are way against that. So the phase shift is just some way of compensating for where you're starting, when time is equal to 0. Because when time is equal to 0, that's zero. And so you're left with sine of the phase shift times epsilon sub naught. Or cosine, whichever one you're using.
The phase shift is gonna be, well, in this case, radians probably.
It would be in radians. From a graph point of view, what the phase shift does is the phase shift will move your graph one way or the other, or it might shift it this way.
Okay.
You want to ask something?
Nope.
Anyone else want to ask something if Jack refuses to?
Wait, so why is the little e down there? Is that just the point we're trying to find on the graph? Is that just the point we're trying to find?
That would be, if my phasor is at that position at the moment we care about, then the instantaneous voltage at that moment is that value right there, that X value.
Yeah. Okay.
All right. So, as I'm going across, I know voltage gains equals voltage losses. So as I go across here, I'm gonna basically, whatever I gain here, I'm gonna lose there. So at this moment for that diagram right there, this also has to be the voltage across the resistor. If we did it out more formally, I know that the change in voltage across the resistor, that's not what I wanted. The power supply plus the voltage across the resistor is equal to 0. This is epsilon minus, that's supposed to be a lowercase epsilon, minus the voltage across the resistor equals 0. Epsilon is equal to, my notation got sloppy there. And so that's epsilon sub naught sine omega t plus phi is equal